Hello, this is an overview of section 4.6, directional derivatives and gradients. If we want to take the derivative of a function that's not necessarily going in the x and the y direction, we want to take the derivative of the function going in another direction, we're going to call on the directional derivative. So we have to establish a direction that we're moving towards. Let's say we'll use the cosine and sine of theta as a direction. And we'll see that the directional derivative, much like the other derivatives, will rely on a limit as h approaches 0. It turns out that if we have a directional derivative, instead of using these limits, we'll find another way to do this, and we'll do this by doing this special formula where we have f sub x of xy times the cosine of theta plus f sub y of xy times the sine of theta. Turns out that this f sub x and f sub y can really form a vector while we're looking at the vector cosine theta sine theta, and this essentially just looks like a dot product of a couple of vectors, and we'll see what those vectors actually mean. In any case, a visual of something like this would be a red vector would be the direction that we're looking at on the xy plane, and then we're interested in finding the slope of that vector that's on the surface tangent to the xy plane going in a different direction from just the x and the y. Well, it turns out that f sub x and f sub y are actually can actually form a vector, and if you put that in vector form, you get what's called a gradient. So the gradient is actually a vector. It's denoted by this upside down triangle. We'll see later on that this is called del, but if you put that with f, it's called grad f. So that the gradient of f is really the f sub x comma f sub y as a vector in 2 dimensions. Well, this was used in the formula for the directional derivative, but it turns out that these gradients are also in its own kind of special. So there are some properties of the gradients that we're going to study. It turns out that if the gradient is 0, then the directional derivative is going to be 0. If the gradient is not 0, then you can find the maximum directional derivative by going in the same direction as the gradient. And you can also find the minimum directional derivative by going in the opposite direction of the gradient. Not only that, the gradient's also perpendicular to a level curve. So if we take a look at this with a picture, we'll see at that point on the surface, to go up the steepest, you would go in the direction of the gradient. To go down the steepest, you'll go in the opposite direction of the gradient. And looking at this in 2 dimensions, if you look at the xy plane now, the gradient happens to be perpendicular to the tangents of a level curve, which is essentially saying that it is perpendicular to a level curve. Finally, we're going to take a look at gradients in higher dimensions as well. The definition is the same as the definition that we've seen. The directional derivative definition and the gradient definition are pretty much the same, except you'll have a third component associated with it. And also, the directional derivative, much like what we saw in the tangent plane, will be kind of like a dot product between the gradient and the unit vector that we're looking at. Okay, that is your overview for section 4.6. Good luck.